the concept of the maximum radar range. The maximum range of a radar system is determined by several factors, including the transmitted power, antenna gain, wavelength, and the radar cross-section of the target. The key limitation is the receiver's sensitivity, S-min, which defines the minimum detectable signal. The received signal, PR, decreases with increasing range, and the maximum range is reached when PR equals S-min. The formula for maximum range involves parameters such as transmitted power, antenna gain, wavelength, radar cross-section, and S-min. Pulse radar systems enhance detection by transmitting multiple pulses and summing the echoes to achieve a detectable signal above the noise floor. This section discusses the concept of pulse integration in radar systems, which refers to combining multiple radar pulses, or echoes, to enhance detection. The number of pulses integrated, N, depends on factors like the radar's receiver sensitivity, the beam width of the antenna, θb, the scan rate, θs, and the pulse repetition frequency, PRF, which defines how frequently pulses are transmitted. As the radar antenna scans, a target remains within the antenna's beam for a certain duration, allowing the radar to collect and integrate multiple echoes from the same target. By doing simple mathematics, the number of pulses integrated can be calculated using these parameters. Let's see in next slide. This section explains how to calculate the number of pulses a radar can integrate while its antenna scans a target. The key idea is that the radar beam illuminates the target for the duration it remains within the antenna's beam width, θb. The scan rate, θs, represents the angle the radar scans per second. To find the time the target is illuminated, divide the beam width by the scan rate, θb by θs seconds. The number of pulses sent during this time is determined by multiplying this time by the pulse repetition frequency, PRF, denoted as Fr. Therefore, the number of pulses integrated is N is equal to θb Fr by θs. This section explains the concept of unambiguous range in radar systems. When radar transmits pulses, it receives echoes from targets at different distances. However, if pulses are transmitted too frequently, high PRF, echoes from far targets might overlap with echoes from the next pulse, causing ambiguity in range measurements. This is called range ambiguity. The unambiguous range is the maximum range where all echoes from targets arrive before the next pulse is transmitted, ensuring accurate measurement. The formula for maximum unambiguous range is R unamb is equal to C by 2 Fr, where C is the speed of light and Fr is the pulse repetition frequency, PRF. The unambiguous range is defined as the maximum distance beyond which a radar target appears as a second time around echo, causing ambiguity in range measurement. It is the range within which all target echoes arrive before the next pulse is transmitted, ensuring accurate and unambiguous detection. In this section, the focus is on the concept of minimum range in radar systems. The minimum range is defined as the shortest distance at which a radar can detect a target. In pulse radar systems, the same antenna is often used for both transmitting and receiving. When the transmitter is active, the receiver must be switched off to avoid damage from high-power signals. This creates a blind spot for the radar during transmission. The minimum range is determined by the pulse width, tau, of the radar transmission. The formula for the minimum range is Rmin is equal to C tau by 2, where C is the speed of light and tau is the pulse width. For example, if the pulse width is 1 microsecond, the minimum range is about 150 meters. While making the pulse width smaller can reduce the minimum range, this also reduces the power of the transmitted signal, which can make it harder for the receiver to detect weak echoes, complicating the system and increasing costs. Therefore, balancing pulse width and power is important, especially in modern applications like close-range sensing. However, for long-range detection, this parameter is typically less significant. This section explains the concept of range resolution. Resolution refers to the radar's ability to distinguish between two closely spaced objects. Suppose there are two objects, A and B, at distances RA and RB from the radar. The radar sends a pulse and receives echoes from both objects. Initially, the echo from object A, at RA, and object B, at RB, are clearly distinguishable. As the distance between them decreases, the echoes come closer in time. The range resolution is the minimum distance between these objects at which the radar can still detect them as separate targets. Range resolution is influenced by the pulse width. Narrower pulses provide better resolution. Initially, resolution is assumed to equal pulse width, but more advanced techniques like pulse compression can greatly improve resolution beyond the pulse width. This concept is similar to image resolution in cameras, where higher resolution provides clearer and more detailed images. In this section, the transmitted power of a radar system is discussed. Radar transmits pulses, and the power associated with these pulses fluctuates over time. The peak power, PP, refers to the maximum power during the pulse transmission, and the average power, PA, represents the average power over time, including the off periods between pulses. The time between pulses is called the pulse repetition interval, PRI, and its inverse is the pulse repetition frequency, PRF or FR. The formula to calculate average power, PA, is derived as PA is equal to PP times duty cycle, where the duty cycle is defined as the ratio of the pulses on time, tau, to the total period, therefore tau times FR. Thus, average power is equal to peak power multiplied by the duty cycle. In radar systems, peak power is critical for detection, while average power is a transmitter specification. Key formula: PA is equal to PP into tau times FR. Or equivalently, PA is equal to PP times duty cycle. This section introduces the concept of PRF staggering, used to resolve range ambiguity in radar measurements. Range ambiguity occurs when a target's distance exceeds the maximum unambiguous range, causing the radar to mistakenly detect the target as being closer than it is. In a thought experiment, the radar observes three targets, A, B, and C, placed at different distances. A is within the unambiguous range. B is between 1 and 2 times the unambiguous range. C is between 2 and 3 times the unambiguous range. When pulses are transmitted, radar receives returns from these targets at different times. Since A is within the unambiguous range, its position is measured correctly. However, B and C's distances appear ambiguous, making the radar think they are closer than they are. PRF staggering involves varying the pulse repetition frequency, PRF, to distinguish between unambiguous and ambiguous echoes. When PRF is changed, the time intervals between pulses shift, causing ambiguous echoes, B and C, to spread over a range of positions, while the unambiguous echo, A, stays at the same position. This method allows radar to identify and correct for ambiguous measurements, ensuring accurate range detection. Depending on the number of ambiguous echoes, 2 or more PRFs may be needed to resolve the ambiguity. In summary, PRF staggering is a technique that varies the PRF to distinguish and resolve ambiguous radar measurements, ensuring correct range detection for all targets. This section discusses the concept of radar cross-section, RCS, a fundamental parameter in radar systems. RCS is defined as the equivalent area that intercepts power and scatters it in all directions, producing an echo at the radar receiver equivalent to that from the actual target. RCS has two main properties. Effective area: it represents how much power the target captures from the radar signal, similar to an antenna's effective area. However, it's not a physical area but an electrical one that depends on the target's shape and orientation. Scattering: unlike antennas, which radiate power, a target scatters power in various directions. The radar is concerned with how much of this scattered power returns to it. RCS depends on the angles of illumination and scattering, as well as the target's shape, size, and material. The unit of RCS is in square meters, m superscript 2, and, when expressed in decibels, is referred to as dBsm. In summary, RCS defines how effectively a target reflects radar signals, factoring in the amount of power captured and scattered back to the radar. Contents covered in this video are: maximum radar range, RMAX; integration of echoes; unambiguous range; minimum range; range resolution; Transmitted power. PRF staggering. Radar cross-section, RCS. This content is taken from 4th and 5th lectures of NPTEL course Principles and Techniques of Modern Radar Systems. Thank you.